Let's imagine that we've got some container with an ideal gas in it. And let's imagine the container's got some volume V. Now these gas atoms, particles, are moving around. They are bumping into the wall, bouncing off the wall like this. Many of these are doing this per second. We've got, on the order of 10 to the 23 atoms or something, or particles in there. They are hitting the walls constantly. They all have some mass, therefore they have some momentum. The momentum is changing. The walls must be exerting some impulse on them. The bottom line is that these atoms must be exerting a pressure on the sides of the wall. Remember, pressure is a force per area. There must be some force being exerted on the wall because the wall must be exerting a force back. So the gas particles must be exerting some pressure on the walls of the container. So my question is, what properties of the gas will affect the pressure? We want to try and figure out what value the pressure might have. Let's see if we can kind of do it at least qualitatively. Well, let's think about this. So the number of particles, or the number of moles, will certainly affect the pressure. The more particles we have in here, the more bounces off the wall we have, the more force is being exerted, the greater the pressure. So we kind of expect that the pressure will be proportional to, and we can either write it in terms of the number of particles or the number of moles. If we double the number of particles or double the number of moles, we would expect twice as many bounces per second, so to speak, and so we would double the pressure. Okay, so that makes sense. Now, what else? Well, what about the volume? If we decrease the volume, then the particles have less room and they'll be bouncing off the wall more often, again, so we would expect an increase in pressure. So we expect the pressure to be inversely proportional to the volume. If you increase the volume, you decrease the pressure. Decrease the volume, increase the pressure. So we expect it also to somehow be related to 1 over the volume. Now, what about the temperature? The temperature tells us something about the kinetic energy of the particles, and the kinetic energy tells us something about the velocity of the particles, and the faster the velocity is, the harder they're going to be bouncing off the wall, the greater the pressure. So if we increase the temperature, we expect to increase the pressure. Well, that is also the case. So the pressure will be dependent on the temperature. But here again, we've got to be very careful. In this circumstance, we have to make sure that we measure the temperature in Kelvin. Because to say, oh, well, 0 degrees Celsius, that means there must be 0 pressure. Well, no, that doesn't work out that way. The temperature in Kelvin is directly related to the kinetic energy, and which is related to the velocity. So we've got to make sure that when we put the temperature into the equation that we're developing, it is in Kelvin. So this is very, very important. It's one circumstance where the temperature must be in Kelvin. Well, it turns out that that's pretty much it in terms of properties of the gas. And we can write this as an equality. We'll bring the V over here, and we'll write this as P times V equals the number of particles or the number of moles. So we'll actually have two forms of this. We can either write this as in terms of the number of particles, or we can write this in terms of the number of moles, and then times the temperature. And then we need to put in a constant of proportionality. And the constant of proportionality, it has the same value no matter what type of gas you're considering. So it doesn't matter what the atoms actually are. That all kind of washes out, assuming that it is an ideal gas, and we end up with the same constant. When we use the number of particles, the constant that we write is a lowercase k. And when we write the equation in terms of the number of moles, the constant is written as a capital R. And the values for these are K is equal to 1.38 times 10 to the negative 23 joules per Kelvin. And the value of R is 8.31 joules per Kelvin, but then also mole Kelvin, joules per mole Kelvin. And these results, they're basically the same equation, just converting, so the difference between K and R is basically just Avogadro's number. So these are basically the same equation, just whether you want to write the numbers in terms of the number of particles and the number of moles. This is called the ideal gas law. Okay, very, very good. Let's stick some numbers in here and see what it tells us. Oops, sorry, forgot just to mention that K is called the Boltzmann constant. This is named after Ludwig Boltzmann, who was an Austrian physicist. And R is called the universal gas constant. Okay, so now let's stick some numbers in the ideal gas law. Let's see if we can figure out how many particles are in 1 cubic meter of gas. So imagine we've got a cubic meter, so 1 meter by 1 meter by 1 meter. And we'll assume standard atmospheric pressure, 1 atmosphere, and room temperature, say 20 degrees Celsius. So what do we get? Well, let's figure out how many moles there are, and then we'll convert moles to particles. We could just use PV equals NKT, use capital N and solve for capital N, but let's figure out the number of moles first. So PV equals nRT, dividing by RT over here. We have N is equal to PV over RT. Pressure, 1 atmosphere, 1.0. We're going to put everything in standard SI units. 1.013 times 10 to the 5th pascals times the volume, 1 cubic meter, divided by R, 8.31 joules per mole Kelvin, times T. Now, remember, we can't put in 20 degrees Celsius. We have to put it in Kelvin. The temperature in Kelvin is the temperature in Celsius plus 273. So the temperature in Kelvin is 293 Kelvin. Divide this out, and what do we get? We get 41.6 moles. Converting this to particles, we've got 6.02 times 10 to the 23rd particles per mole. Moles cancel. Oh, let's just notice here. We've got, let's look at the units here. We've got Pascal is, let's see, how do all these work? Pascal is a Newton per square meter. Multiplied by meters cubed, the meters squared will cancel 2 of those, just leaving meters. A Newton times a meter, that's a joule, so a Newton meter cancels a joule. We've got Kelvin divided by Kelvin, the Kelvins cancel. We've got 1 over moles, which brings the moles up to the top, so we end up with units of moles, and that works perfectly. Okay, so we've got 41.6 moles times 6.02 times 10 to the 23 particles per mole. Moles cancel, and we end up with 2.50 times 10 to the 25 atoms, and then that is, what is that? That is capital N. So little n, 41.6 moles, capital N, 2.5 times 10 to the 25 atoms. Okay, very, very good. What we're going to do now is we're going to go back to the ideal gas law, and we're going to look at some of its properties for specific processes. In other words, let's imagine we've got this gas, but that we can manipulate some of these values. What does that tell us about how the system will behave? Well, let's take a look. Let's imagine that we've got a container here with a piston, and this piston can move up and down, but makes a seal on the edge. So we've got some volume here, and we're going to put some ideal gas in here. We're going to assume we've got some number of particles or number of moles of either one of ideal gas in here. So here's our ideal gas. But we can move this piston up and down, so we can vary the volume of the gas. One thing we're not going to change is we're not going to change the amount of the gas. In other words, we're not going to change big N or little n, the number of particles or number of moles. We're going to assume that that stays constant. But as we move the volume up and down, as we move the piston up and down and change the volume, the pressure of the gas, that could change. The temperature of the gas could change. Let's imagine, so the pressure, we can vary the pressure by maybe putting more or less weight on top of the piston, so that would push the piston down more, or we remove some of the weight that allows the piston to move up, and we can change the pressure that way. Also, let's imagine that we can heat this up. Maybe we put a candle under here or something like that, a burner, or we pack ice around it or something like that, so we can change the temperature of the gas as well. So we can change anything we want of the values for the ideal gas, except the amount of gas, in other words, capital N or lowercase n. So what we have is this is going to be described by the ideal gas law, PV equals NKT. And what we're going to do is we're going to look at how do the other values vary if we change something. Well, assuming N is constant, and K, well, that already has a constant value, the only things we can change then are, or that we're going to change, right? We could change the number if we wanted, but for now we're going to hold that fixed, constant. We can change the pressure, the volume, and the temperature. Well, let's start out with the temperature. Let's imagine that we don't change the temperature. We hold the temperature fixed. What kind of process, what kind of changes can the ideal gas undergo, assuming that we hold the temperature fixed? Let's take a look.